Yes, I'm actually recording. Okay,
Nice.
so a reminder from what we did last time. So the summary of the previous meeting was that we motivated the study of matrices using linear transformations, which are functions that have these nice freshman's dream type properties. Then we saw that if you go up in dimension to 2, every linear transformation in 2 dimensions is determined by 4 numbers, which we put into a matrix. And we studied function composition, kind of the most natural thing to think about. When you have a bunch of functions, you start composing some of them and saw that this has the interpretation of matrix multiplication. And we saw the nice mnemonic for multiplying matrices that pairs up horizontal and vertical lines. And importantly, that multiplication is non-commutative. So these are the punchlines from last time. Questions about any of these things?
I have no questions.
Okay, good. It seemed like you still find it pretty easy based on I mean, the first Matrix challenge you didn't have any trouble with, right? So is this all still pretty simple and intuitive?
Yeah.
Good. Okay. So what shall we do today? So you might try to generalize if you think a matrix is something which takes in a vector and spits out another vector, and you computed some of those on the first challenge, for instance, to see the image of the unit square, it usually, in general, turns into some parallelogram. So you can think of that as taking individual vectors and mapping them into individual images. So now you could ask, what happens if you try to visualize the action on all of the points in the plane at once? So just imagine a bunch of vectors and seeing the way the matrix acts on all of those simultaneously. That'll be the first thing we do, and we'll look at some nice pictures to get some intuition for that. That will lead us to think about the idea of the determinant. So the two most important numbers associated with a matrix are its determinant and its trace. So we'll see what those numbers are and what they do. The determinant will lead us to think about the inverse function. I think you asked about this last time. If we know there's a lot of very standard questions you could ask about functions, like do they have inverses? You could ask those questions about matrices, and the determinant will give us an interesting way to characterize whether an inverse function exists. So then our last goal will be to understand if there is no inverse, what does that mean geometrically in terms of looking at pictures in the plane, and what does that mean algebraically? So this is where we are headed today. Thoughts or observations on the roadmap?
I do not have any thoughts or questions.
Sweet. All right, onward. Let's look at some pretty pictures then. But first, just to remind us before the pictures of the way that a matrix acts on individual vectors. So we're going to look at this matrix which is diagonal. The only non-zero elements are in the top left and bottom right. And just to warm up, what is the action of this matrix on the unit vector along x, 1, 0? What does that give us?
That will be to do. We have 3/2 in the first place and 0 in the bottom.
Good. And then what does that matrix do to the unit vector along y, the 0, 1 vector?
This will be, let me think, 0 on top and 3/2 on the bottom.
Good. So all we've done, I'll draw the first one. The unit vector along x started out like this, the purple one, and then we multiplied it by the matrix, and it just got longer. It still points along the x direction, but it got mapped into a vector which is 3/2 as big. And similarly, we started in the second slot, we started with a vector that points along y and has length 1, and this vector similarly scaled that up, so now it's 3/2 as long. So you can kind of see what this is going to look like if you imagine it acting on all of the points in the plane at once, because it's taking these vectors and stretching them out. All of the vectors are uniformly stretched by a factor of, say, 150%, or 3/2. We'd like to visualize that for the whole plane. So what happens if you think about this matrix scaling by 3/2, multiplying every vector in the plane simultaneously? So what does that do? Here's the picture. Now we want to go slowly through this. So we start with the blue. So try to block out the green first and just look at the blue grid. So here's the origin down here, the black point. So if you think of the blue grid as the original plane, so for instance, this is the vector of length 1 along x in the original plane. Here is the vector of length 1 along y in the original plane. And you can kind of look at all the other lattice points, these grid points that are other vectors in the original blue plane. Then we just take this matrix, 3 halves on the diagonal, and apply it to every single point in the blue plane. So we stretch all of them by 3 halves in both directions. That gives us the green plane. So you could see that this purple vector pointing upwards, which was 0, 1 in the old plane, as we saw in the previous slide, is stretched up to 3 halves, and the x one is also stretched up to 3 halves. And there's some shapes as well, so you can see this square, the unit square in the plane, which is, well, I guess this is not the unit square because it's length 2 on a side in the way that we've drawn it. So there's this square with length 2 on each side, which is stretched up to the green square, and there's this other weird shape over here, which is similarly stretched up and going from blue to green. So I claim that in going from the blue to the green, all of the lengths, like the length of this square on one side, was increased by a factor of 3 halves. Every length was simply multiplied by 3/2. So my question for you is, if we increase every length by a factor of 3/2, by what factor do areas increase in going from the blue to the green?
I believe this is 9/4.
Good, 9/4. Simply because area is length squared. So every area is going to be scaled up by 9/4. So this is kind of similar to the first matrix challenge where you multiplied by a matrix that I believe looked like 2, 1, 1, 0, and you saw that the unit square, which had area 1, was sent to a parallelogram with area 2. So somehow this matrix multiplies areas by a number which is 9/4. This matrix multiplies areas by a number which happens to be 2. And other matrices will multiply areas by different numbers. We want to try to understand some more examples to see if we can guess the pattern for what determines the area scaling. Okay, does this picture make sense, and/or are there thoughts?
I have no thoughts or questions. This makes sense.
Good. It's very, very geometrical and pretty intuitive. Okay, here's a different matrix. You'll study this in problem 1 of Matrices Challenge 2. Since you could think, if you could ask if matrices just kind of transform all of the points in the plane, you could ask what matrix rotates the plane. We know that you can just rotate the plane by some angle. And it turns out that for any angle theta, you take a 2x2 matrix that has cosine of the angle, minus sine of the angle, plus sine of the angle, and cosine. So for instance, let's try this with pi/6, or if you're a heathen, 30 degrees. So you can pretty intuitively see that all of the points, so for instance, you could start with this vector 1, 0, and it's rotated by 30 degrees to this one, this new vector, which I guess would have the coordinates √3/2, 1/2, right? Cosine and sine of 30 degrees, or pi/6. And similarly, all the other shapes are rotated uniformly by 30 degrees or pi/6 about the origin. So you don't need to prove this, but just kind of using intuition or your expectations, if you asked the same question we did on the previous slide, are the areas of shapes increased, decreased, or unchanged under the map which rotates the plane?
Well, just based off how it looks, I'm gonna say unchanged.
Good, okay. Can you unpack any intuition for why you think that might be true for rotations?
I'm pretty sure this is going to be a total guess, but I'm going to say because the values in the positions 1 and 4 are the same yeah. I'm just going to say that values in 1 and 4 are the same.
Ah, you're saying the top left and the bottom right, these things?
Wait, no, that was true last time.
Yeah.
And it changed.
Yeah, it's hard to tell just by looking at the matrix, but intuitively, if we just knew this was a rotation, then you'd probably be able to guess that the rotation shouldn't change the areas simply because, I mean, if you tilt your head looking at a figure in the plane, that's kind of implementing a rotation, and it shouldn't change the area physically. So if we knew this was a rotation, we'd probably be able to guess that the area should be invariant. But that's not a proof that this matrix is going to leave areas invariant. So we'll have to develop a few more examples to see why that's the case. But do you agree with I mean, this is still non-rigorous, but do you agree with the intuition that we should not expect a rotation to change areas?
Yes.
Good. Okay, let's look at some more. I think I have 2 more pictures, or maybe 3. Okay, similar thing. You could probably start to see the pattern. This is a reflection. So it's going to multiply the x component of every vector by -1. So you can kind of see this is going to take, whoops, it's going to take a vector that points, say, 0, 2 is going to get mapped to 0, -2, and maybe the vector that goes all the way up to this point is going to get mapped to its image, which is simply reflecting across this line. So this matrix simply reflects about x equals 0. So same question. Do you think areas are increased, decreased, or unchanged?
Unchanged?
Good, yes. So reflection, similarly, looking in the mirror physically should not change any areas. But we're starting to see some patterns in the elements of the matrices that relate to whether the area is changed or not. But good, let's develop maybe 2 more. How about a shear? This is a bit harder. So a shear is kind of moving everything in a slanted way to the right. So this takes the vector, for instance, we could do an example. So 1, 5/4, 0, 1 acts on the vector, say, 1, 1, which points, at 45 degrees up in both x and y. This is sent to 1 plus 5/4, which is 9/4, and 1. So you see that this vector is sent to a vector whose x component, or sorry, yeah, the y component is the same. The lower component, 1, is the same, but it's stretched along x. So it's sent over here to something like 9/4. So this is harder to tell, but what do you think about the areas? You can kind of tell by looking at this square has area 4, and it gets sent to this parallelogram. But what do you think? How do areas change for a shear?
Just based off of looking at where the green points of the grid are on the blue grid, it looks like the area has increased since the parallelogram isn't at 45-degree angles in the upper left corner, the green one.
Good. It's hard to tell, yeah. So if we looked at the parallelogram, let's see, the area of a parallelogram is its base times its height. So the base of this parallelogram is length 2. I think the height, so you measure the height from the base to the projection of the opposite side. So the height is still 2, actually, even though it's slanted. So the area of this parallelogram, you could see why this formula works by kind of chopping off one side and moving it over to turn it back into a square. You could just imagine slicing and rearranging. But the area of this parallelogram is still 4, actually, which is the same as the square its pre-image. So surprisingly, even though it's hard to tell by looking, you see what I'm saying with the area?
I see. Because if you take the right side and add back on, you still have something going over. That's the little bit I wish I could draw onto your screen that gets added again since it's going over.
Yeah. It's. I think I understood what you were saying, even though it's hard to explain. You're saying that if I slice like this and then kind of took this guy here and moved it over, it doesn't quite fit, but you could see that if you glue this bottom right edge onto this guy and then do, I think, one more rearrangement because of this corner, you can kind of cut and paste to show that the area of the parallelogram is the same as the area of the square. That's what you're getting at?
Yeah, I forgot about my formulas.
Yeah, that's fine. I mean, memorizing formulas is not always useful. So good. So this one's unchanged, even though it's hard to tell by looking. So This is another example of where, uh, I mean, intuition can lead you astray. I think intuition is often very good for seeing what you expect the answer to be, but then you have to hold it accountable, as Hardy says, which means check whether the intuitive answer is actually correct. And if you do this often enough, it will actually change your intuition, so it starts being correct more of the time. Good, I think this is the last one. So this is very similar to the first one, except it's 3/2, and instead of 3/2 in the bottom right, it's 2/3. So you can see that this is now asymmetrical. The x vectors, so for instance, this guy is sent to a longer version of himself. The x guy is stretched, but the y guy, that's not where the blue one is. The y01 is sent to 0 2/3, so he's shrunk. Now this is quite hard to, I mean, you could do the same, I mean, maybe you could look at this rectangle and say, well, this is the image of 0 2 under this. 0 2 is sent to 3, right? And then this is the image of 2 under this matrix, so 2 times 2/3 is 4/3. Giving it away too much, I guess, but what do you think? Do you think areas are increased, decreased, or unchanged for this squeeze map?
I believe that this one is unchanged.
Yeah, good. And this is because, well, you can see from the square and rectangle, 3 times 4/3 is the same as 4, but more generally, you might think, oh, it's because these two different factors were chosen precisely to multiply to 1, right? We squeeze in one direction just enough to compensate for the stretching in the other direction. And then that's exactly why this one preserves areas. Okay, I think this is the last picture. So questions before we try to formalize the intuition from the pictures?
I have no questions.
Cool. Okay, now there's just a giant slide of math.
Oh,
Okay.
great.
Good. Oh, this isn't that bad. So you can ask, can we find a general criterion, just some way of looking at a matrix and immediately telling how do the areas transform, so we don't have to draw pictures and guess? And the answer is yes. And I'll tell you what the answer is. You take any 2 by 2 matrix, you start with M, which is A, B, C, and D. The answer for the area of the image of the unit square, so you take the two vectors 0, 1, and 1, 0, determine that square, and then see where they go. That area will always be given by the absolute value of the top left times the bottom right, which is AD, minus top right minus bottom left, BC. And this is the determinant. So the thing inside the absolute values we will define as the determinant of M. I usually use an equal sign with 3 bars when we're defining something for the first time. So this is defined as AD minus BC. And if you remember some of the examples, you can see this matches most of our well, all of them actually. The 3/2 and 2/3 with zeros. This works because 3/2 times 2/3 is 1 minus the zeros. The rotation had cosine, cosine, minus sine, sine. And that did not change areas, which is good because cosine times cosine is cosine squared, and you subtract minus sine times sine. The two minuses give a plus, and what is cosine squared plus sine squared of any angle?
Don't forget about the absolute value in your definition.
Wait, what'd you say? The absolute value?
In the triple equals.
Yeah, the determinant is the thing inside the absolute value. So this is the absolute
Okay.
value of the determinant.
That makes more sense.
Yeah. The determinant can be positive or negative, but we're going to define areas to always be positive.
Oh, okay.
Okay. So let's see how to prove this. This will be a little bit of work, but let's find the parallelogram we get by applying this general matrix to the two sides of the unit square. There, the two of the four sides. So what do I get in this first line, equation 1? When I apply a, b, c, d to 1, 0, what do I get?
You get A1 in the top and C1 in the bottom.
Yeah, so a and c. And when I multiply by 0, 1, what do I get?
B, D.
Yeah. It's just a general rule that if you multiply any 2 by 2 matrix by 1, 0, it's always going to give you the first column. And if you multiply by 0, 1, it always gives you the second column. That's pretty fast. Okay, so one quick comment now. I'm going to draw these two vectors, because we're trying to find the area of the parallelogram spanned by these two vectors. I need to draw those two vectors in a particular way where one of them is oriented clockwise of the other, right? I have to pick one. I have to pick one to be clockwise of the other to draw the parallelogram. So I'm just going to say, assume without loss of generality that the first one, AC, is the one that is at a higher positive angle. So I'm just going to assume that the one which is counterclockwise of the other is AC, and the one which is clockwise of the other is BD. If that's not true, then just switch the names of the variables A with B and C with D. That won't change our answer because of the absolute value. If I swap A with B and C with D, then AD becomes BC, and BC becomes AD. So I've just switched the two terms, which I'm subtracting, which means there's a minus sign overall. But since we take an absolute value, that doesn't change the result. So that's why we can assume that one of these, the one that's counterclockwise of the other, is going to be AC, and swap them otherwise. It's actually an important point. We'll come back to that in a bit, because there will be one small subtlety about this sign. But for now, I claim that we can just pick one of them to be counterclockwise of the other. Okay, this is the setup. Questions about any of this?
I have none.
All right, now we have to do some geometry to find the area of this parallelogram. It's going to be pretty fun. So I drew it on paper before. So you're going to help me work through labeling all of these. So as I say, one of the vectors has to be counterclockwise. So I've drawn AC to be the one counterclockwise, BD to be the one down here, and their sum. So their sum is A plus B comma C plus D. And then I put dotted lines on all of these places because I want to label all of these lengths. And the reason for that is to find the area of this parallelogram, our strategy is going to be to find the area of the rectangle which comes from joining all of these outer dotted lines to make this big rectangle. And then we'll subtract off everything outside the parallelogram. So we'll subtract off all this stuff, which I'm shading in pink, but I'm going to immediately unshade because it's very messy. Okay, so I'll label the first one, the big outer ones for you. So this height is the y-coordinate of this A plus B, C plus D vector. So this y-coordinate, which is the big height, is C plus D. This big x-coordinate is A plus B. Okay, so now let's start labeling other stuff. So how about this down here in the bottom left? What is this length, which is kind of the length of this rectangle?
A.
This is A. Good. What is in the bottom right, this length? Let's see, it's the difference between...
Would that be the absolute value of A minus B?
Yeah.
Or am I thinking wrong? No, it's just A plus B. What am I saying?
Well, A plus B is this x-coordinate, so it's A plus B minus this x-coordinate, right? So A plus B is the whole thing, subtract off B, so I think this guy should also be A down here. Right?
Okay.
What's this height?
That will be D.
Good. And what's this height?
By the same logic, that is also D.
Let's see, D, yeah, okay. So then I'm just going to symmetrize across here. D and A. Alright, I think now it's basically everything we need. Okay. So, alright, so the areas of these 4 rectangles on the corners, what is that total area from all 4 of them? So area of 4 rectangles, what's that going to be?
Or AD.
Good. I think, actually, I forgot. Yeah, it's easier. Yeah, we could do that. I'm going to use two of them actually. So I forgot that. Let's let's take the area of these two rectangles because then I want to find the area of this triangle, right? So I actually made a mistake. We want two of these, so 2AD. Good. So 2AD is these two top left and bottom right rectangles. Now let's find the area of this blue shaded triangle. So this thing is also outside the parallelogram. So what is the area of one of the blue shaded triangles? I didn't actually label both of them for you. You also kind of need this. Maybe you can see what that is. Well, it's a half base times height, but what are the bases
Yeah,
and height?
I was gonna half C times A.
Half CA, good, yeah. Because the base is A, and as you saw, the height is, well, if the whole thing is C minus D, and we chop off the D, we're left with C. So that's a half CA. There's another one of those triangles, the same one on the other side, which I'm also shading in blue here. And for the same reason, this whole thing is C plus D, so its height is C, and the base is A. So there's going to be two of these. I'll just rewrite it. So there's two of these triangles that we have to subtract, which is just going to be CA. Now we're almost done. We just need to subtract off this triangle. Oh, I shouldn't use the same color. That was bad. CA. Gold. Okay. So this triangle down here and this triangle up here. So if we got that, we're done. Because now you could see we've shaded all of the area which is outside the parallelogram, right? We're trying to find the area of the parallelogram. So if we get these last two gold triangles, then we're in business. So what is the total area of these two gold triangles?
I believe it is B times D.
Good, yeah. This is A minus B minus A, or sorry, A plus B minus A, so the base is B and the height is D. So two of those give BD. Good. Finally, what is the area of the big bounding rectangle that contains the parallelogram plus all the other junk?
A plus B times C plus D.
A plus B, C plus D. Good. Okay, now we just have to do some algebra. This is one of the... Oh, I can't slide, can I? Interesting. Okay, well, I'll see where... how can I do this? I don't have any more space, but... Okay, well, I guess I'll just go to the next one. Are you happy with all of these calculations so I could erase them and then do the subtraction on the next slide?
Yes.
Okay, good. So yeah, the strategy is pretty simple. Just have to be careful, right? We just found all these areas, and now we're going to subtract them off. Good. I mean, I'm actually just going to go to where I've labeled them for you, so hopefully we got the same answers. Here I've just shaded in red the half AC you told me, the half BD, and there's two of those, and then the ADs on the corners. So let's do the subtraction for the whole thing. You say area of the parallelogram should be the area of the big square minus, well, what are all of the contributions of the shaded things? Well, we have to subtract 2AD for the rectangles, then we have to subtract a BD for the two blue triangles, and subtract an AC for the red triangles. So the A big, as you say, is quantity A plus B, quantity C plus D. Still subtracting, minus 2AD minus BD minus AC. Foiling out, AC plus AD plus BC plus BD minus 2AD minus BD minus AC. Now we get some cancellations. BD cancels with BD, AC cancels with AC, and we're left with AD minus 2AD is minus AD, so BC minus AD. Okay, and recall we're comparing this to, compare to absolute value of AD minus BC, which by definition is the absolute value of the determinant of the matrix M. So our area is going to be equal to what we claimed it would be, assuming that BC minus AD is positive. Right? If this is positive, then this is negative, and the absolute value of that negative number will give us the desired area. So this is the sign subtlety. We're going to come back to this on the next slide to understand why we have the sign backwards from what you might have guessed. And there's a deep reason for that, actually. But just for the moment, let's not worry about the sign and just check whether we understand the rest of the argument. So up to the sign, is it clear how we got the area of the parallelogram, which is the image of the unit square?
Yes.
Good. Any other questions or thoughts on this calculation?
I have none.
Okay, good. So that number emerged pretty naturally. Okay, so that up to a small sign issue proves our proposition, and I'm just reminding us AD minus BC is this thing we're calling the determinant. So this tells you the area scaling factor. So now the challenge, I'll draw a picture to help you with the challenge, but I'll ask you to propose why you think we got a minus sign. So why did we get minus the determinant of M in the last calculation? And to help you, I'm going to remind us of the assumption that I made. So we started by taking, let's see, maybe red. So we took the image of the two unit vectors 1, 0, and then maybe in a different color, 0, 1. And then we map this with the matrix into new unit vectors. And, well, not unit vectors, new vectors, period. And then I said assume that the one which is oriented counterclockwise of the other was AC. So let me just draw the colors a bit more suggestively. So the assumption I asked you to make was that this vector was AC, and the vector which is oriented clockwise was BD. And if we remember where these two numbers came from, it was that the matrix M applied to 1, 0, which was the x vector, was AC, and in blue, the matrix M applied to 0, 1, the y direction, was BD. So this is the setup. We mapped these vectors into their kind of tilted versions in the parallelogram, then we found the area, but we got a minus sign. So let's see if you can guess the pattern. Why, there's something a little funny here about the map that we've done. There's something kind of counterintuitive about the way that I asked you to make the assumption about the orientation. Can you guess what's funny about this map?
It really, actually, what you said without loss of generality, so never mind, I was going to say something.
Yeah, but remember the without loss of generality was that if this were not true, so if BD and AC were oriented the other way, then I asked you to just rename the symbols. So if it were not true, we would have taken the matrix ABCD, and in the proof we would have renamed it to BCAD. That was the argument for without loss of generality. So if it were the case that BD were up here and AC were down here, then I would have asked you in the proof to swap the two columns. And if you swap the two columns, then m of 1, 0 would have been BC, and m of 0, 1 would have been AD. Right? That was the without loss of generality argument. So there's something about the order of these two, the swapping of these two vectors, which is giving us a sign in the answer for the area. We're getting what we call in math a signed area. So let's see if you can, you can free associate any ideas that come to mind, but can you see why there's something somewhat strange about the map in going from the left to the right?
The y1 and x1 vectors just swap, quote unquote, swap places relative to each other.
Yeah, the order is reversed. This is very important, right? So in the old pre-application of M picture, then the red vector is oriented clockwise of the blue vector. Then I asked you to assume without loss of generality they were oriented this way in the image. In the image, the red vector is oriented counterclockwise of the blue vector. The order is reversed. So determinant remembers the order of the two vectors as you go around with increasing angle. Determinant remembers which vector do you hit first and which vector do you hit second as you go around with increasing angle. So it knows which one is oriented clockwise or counterclockwise of the other. If you switch the two vectors, determinant gives you a minus sign. So it gives you a number whose absolute value is the area, but whose sign encodes whether the two vectors have been kept in the same orientation or if they've had the orientation reversed. One way to visualize this is you think of the area of a parallelogram that also has some direction around it. So for instance, you could think of a parallelogram with arrows around the side. And you can say, this thing has a positive area. But if you have the same parallelogram with the order reversed, so that you're going now clockwise around the outside, this thing has a negative area. So there's a deep reason for this if you generalize to higher dimensions for why determinant is giving you a signed area. But I don't know if I can make that totally clear based on what we've seen so far, but good. This is kind of subtle, so you should ask questions on this.
I don't really see any questions to ask.
Is it no questions because it's totally clear or sufficiently confusing that it's hard to formulate a question?
I mean, I feel like there isn't much to be asked about negative area.
Okay, that's fair. As long as it's clear, at least from the computational perspective, that determinant can be positive or negative, but the absolute value of the determinant will always give you the area. So that's the key takeaway, I think. Okay. Good. Next. Okay, so I've told you this is where I should back up a bit. So if there's a matrix, I don't know, A, capital A, which is A, B, C, D. Usually, and I mean, you're going to get another earful of my shitting on high school pedagogy, but normally when you learn about matrices, someone will say, without any further comment, here are two interesting numbers you could compute that are associated with that matrix, the determinant and the trace. And the determinant is AD minus BC, and the trace is just the sum of the two elements on the diagonal, top left, bottom right. And they won't tell you anything about what these are. They won't even tell you the determinant is giving you the area scale factor. Then they'll just give you a worksheet where you compute a bunch of these. But I don't really believe in that, so I think I've tried to explain what determinant is doing. It's the scale factor for areas. Trace is much harder to understand. You can either think of it as a sort of average over an orthonormal basis, which is not something we've discussed, or if you know some calculus, you can think of this in a particular limiting sense. So I'm going to try to explain the second of those, the limit sense for the trace. So that's where we're going next. It'll be a bit subtle, and we'll have some limit calculations. But first, before we do that, I have to introduce this identity matrix. So we use the capital letter I for the matrix with ones on the diagonal and zeros elsewhere. Now this has the property that if you multiply the identity matrix times any vector u, I will ask you, what is the result if I multiply the identity by any matrix u, or sorry, any vector u whatsoever?
Is it simply u1, u2?
Yeah, so it's u1, u2, which is just the same vector u back, right? So you hit some vector u1, u2, and you get u1, u2 back out. So the identity matrix acts like the number 1, since multiplying 1 times x for any x gives you x in the real numbers. The matrix the matrix I acts like 1 for vectors. You multiply this times any vector, and you get the same vector back. So what's the determinant of this identity matrix?
It is 2.
It is 1 times 1 minus 0 times 0. Right?
Oh my god.
Good.
How did I mess that up?
You can also think geometrically, because if this doesn't change any vectors, it sends every vector to itself, then when you take the square and hit it with I, you get the same square, so the area is 1, right? So determinant's 1. All right, now this might not sound like a very natural question to ask, but I'll try to motivate it anyway. You could ask, how does the determinant of this identity matrix, which is 1 by default, how does it change if you add a small matrix to the identity? What do I mean by that? More precisely, you take the identity, which has determinant 1, and then you add epsilon times some other matrix A, which can be any A, B, C, D whatsoever. We can ask, how does the determinant change with this perturbation? I use the word perturbation if we're thinking of it as a small change. So we're going to take a limit where epsilon goes to 0. So this is the question we're going to investigate. It's very basic perturbation theory, and you will almost certainly object to this. You will say, why do we need to assume epsilon is small? I can write down this matrix exactly, right? I take 1 plus epsilon A, I take 0 plus epsilon B, I take 0 plus epsilon C, and I take 1 plus epsilon D. I can write this down exactly, and I know how to get the determinant. I take top left times bottom right minus top right times bottom left. So I can get the exact answer. I don't need to make any assumptions about epsilon being small, so why are we doing this? That's a very natural question. My answer is that this is a toy example. So in this case, we can get the answer exactly, but we're going to try a more fancy-looking approach, some fancier-looking technology, which seems unnecessary, but in more complicated cases, either higher dimensional matrices or cases, well, the most common case in string theory is when you have infinite dimensional matrices, so it's very hard to write down the determinant of an infinite dimensional matrix. In those cases, we have to use this technology of perturbation theory instead, because it's really all we have. So the answer to the objection which you might have is that, yes, we don't need to use this tool in this case, but I'm going to use the tool anyway as a toy example just because it illustrates something which is useful elsewhere. Okay, questions on that? Does that sufficiently convince you that the objection can be ignored for the moment, or what do you think?
I'm just going to go with it, because that's the purpose of a toy example.
Okay, fair. Good. All right, so let's see what happens with the toy example then. All right, this is what we're going to do to perturb the identity. So we're going to think about this function, determinant of the identity plus epsilon times a matrix A. But this looks very complicated. It looks like this is a complicated function which depends on the matrix A, depends on I, which happens to be the identity, depends on epsilon. But I'll ask you to think of this as just a function of one variable. f of epsilon. So pretend A is fixed. A, B, C, D, they're all constants, which we know. The only thing which we change in this expression is epsilon. So it's just a function of one variable. As we perturb the determinant, we want to try to measure how sensitive is the determinant to a change in epsilon. How sensitive is it? So if you think of this as some graph where here's the function f of epsilon, and then here's epsilon, maybe this function is doing something very complicated near 0, but we're just going to try to find, if I'm near 0 and I change epsilon by a little bit, so maybe I go to the left a little bit and I change epsilon, how much does the output f of epsilon change? That's what we're going to try to see. So you change epsilon by a little bit, maybe a delta epsilon, and then we're going to see how much delta f, which looks very much like a slope, right? So we're going to see how sensitive is the function f of epsilon to a small change in epsilon. Okay, that's the idea. So I'm going to use the word slope in quotes because, I mean, all of these words in quotes are formally meaningless, so you could very easily object and say you haven't defined any of these. So the words in quotes, I agree, are meaningless, but I'm going to replace them by symbols that actually do have meaning. So if these make you uncomfortable, just ignore the things in quotes and look at the symbols. So to find that slope, we do the usual thing. I mean, what you learned in algebra. For a line, for instance, the slope is the change in y over the change in x. Or if you don't like capital deltas, maybe that makes you uncomfortable. Maybe y2 minus y1 over x2 minus x1. Sure. So that's the slope we're going to get. So what's Oh, sorry, go on.
I see delta, like capital delta, a lot because I play Kerbal Space Program.
Ah, good. So you are not made
Specifically
uncomfortable.
delta V.
Yeah. Delta V is AT, perhaps, for constant acceleration. Good. Okay. Well, good. Then I can use deltas. So the change in the output, what do I mean by change in output? I mean the output when you perturb by epsilon. So the f with a non-zero epsilon, so determinant of the identity plus epsilon a, minus the analog of y1, which is determinant without the perturbation. So you take output with the change minus output without the change. I mean, that's what we mean by change. Then the bottom change in input, well, we're thinking of this as just a function of epsilon. So the change in the input, well, here the input is epsilon. Here the input is 0 because there's no epsilon. So it's epsilon minus 0. So this would be the slope for some finite epsilon. We want to take epsilon small, so I'm going to wrap this entire expression with a limit as epsilon goes to 0. So the thing that we're going to try to compute is this giant expression in brackets. The limit as epsilon goes to 0 of det I plus epsilon a minus det I over epsilon. Okay, lots of stuff. Again, probably seems unmotivated and out of nowhere, but is the idea okay, or do you want to talk more about any of these steps?
I have no problem with what is going on here.
Okay. Then let's expand this then. Okay. So now I will do the objection you may have had at the beginning, which is explicitly computing this, just to see what this thing is going to look like. So the matrix I wrote down 2 slides ago where we explicitly took I plus epsilon a, so this is just the matrix I plus epsilon a, b, c, d. So I wrote that down. The determinant is top left times bottom right minus top right times bottom left. So here's top left, bottom right, minus top right, bottom left. So we get epsilon squared bc. I FOIL out this thing, which gives me a 1 plus epsilon d plus epsilon a plus epsilon squared ad. I factored out the epsilon a plus epsilon d. They have a common epsilon factor. Put the epsilon squared ad along with this epsilon squared bc together in a common factor. The reason I've packaged them this way, because these are the 2 familiar numbers which, well, not familiar yet, but the things that I am trying to motivate is familiar. These are trace A and det A. Good. So this step is just algebra. Is this calculation okay, or should I show some intermediate steps?
I would like to see the bit on the right that eventually becomes det A.
Stuff. So where did this come from, you're asking?
Yes.
Okay. So when you expand out the FOIL, you get 1 plus epsilon A plus epsilon D plus, when you take these two on the outside, you get plus epsilon squared AD. And then you have to remember this minus epsilon squared BC at the end. And then the piece which became determinant just came from factoring out from those two terms, one from the FOIL and one from the final term. Factor out an epsilon squared.
Okay, I'm cool with that.
Good.
I see where the other bit came from.
Yeah, this came from the two cross terms from FOIL, the O and I. Okay, so let's just plug that in. Now we have this expression for det I plus epsilon A, which I'll put for det I plus epsilon A in our strange limiting slope formula. So that whole expression here, maybe I should just circle. I just plugged it in here, and we have to remember to subtract determinant of the identity, but you told me a couple slides ago that the determinant of the identity is 1 times 1 minus 0 times 0, so that's 1. So we subtract 1. Good. Now there's one more step in going from here to here, which I've done, and this is just, the reason we could do this is that you remember that the value of a limit is insensitive to what happens at the point, right? So for instance, a while back when we were studying, say the limit as x goes to 1 of x squared minus 1 over x minus 1, in that case you would have said this is the limit as x goes to 1 of the factored form x plus 1, x minus 1 over x minus 1, and you would say that I'm allowed to cancel these factors top and bottom as long as x is not equal to 1. That's the only case I can't cancel. I can't cancel if x equals 1 because that would be 0 over 0. But the value of the limit does not care what happens at at x equals 1. So I'm allowed to make that cancellation and write limit as x goes to 1 of the rest. Right? So that's what we saw before. I'm going to do something very similar here, because after canceling the 1's, the top has a common factor of epsilon in both terms, epsilon and epsilon squared. So epsilon times a plus d plus epsilon squared times ad minus bc. So as long as epsilon is not 0, I can cancel out one factor of epsilon from the first term with the denominator, and cancel out one factor of epsilon in the epsilon squared to reduce that 2 to a 1. Now again, I can't do that cancellation if epsilon equals 0, but the limit doesn't care what happens at epsilon equals 0, so I am allowed to make that cancellation here. And that's what I've done to go to the second line. So when you cancel that thing top and bottom, you're left with just a plus d, because the epsilon coefficient got canceled, and then you have one more epsilon left on the determinant, ad minus bc. Okay, maybe I should erase the canceling I'm doing so you could see what happened, but do you buy this argument that I can do that?
I do.
Okay. Good, last step. Now we can apply our powerful theorems. We've proved in calculus that all polynomials are continuous. And this, if it's not clear this is a polynomial, just think of replacing the dummy variable epsilon with x, right? If epsilon were x, this would just be some number plus some other number times x, which is clearly a polynomial in x. We know all polynomials are continuous. If a function is continuous, the limit is equal to the function value at that point, which means we can simply plug in epsilon equals 0 to this polynomial and conclude that the answer is a plus d. So are you happy with that step, the continuity argument?
Sure.
Good. Is Shore sarcasm because it's actually unclear, or is it totally obvious?
I understand.
Okay. All right, so good. That's actually the end of the calculation. So the whole upshot of this is that this pair of numbers, this sum of the diagonal elements A and D, which I kind of stated without any explanation, is an important number called the trace. Now we've kind of seen it emerge naturally. I mean, I don't know if you think it's natural. I think it's very natural because, once you've seen this a billion times, limit epsilon goes to 0, det I plus epsilon A minus det I over epsilon equals trace A. So this thing, which is a certain kind of slope that measures how much does the determinant change if you wiggle a matrix near the identity by a small number epsilon. This thing measures that slope. That slope is the trace. So it's kind of an abstract argument. I just want to have some motivation for why this number is important. In Matrices Challenge 2, you'll prove a basic property of the trace, that trace of a product is the same as taking the trace in the other order. So even though matrices don't commute, the trace of matrices commutes. So there's some nice properties like that. And trace will come up also in Matrices Session 3 when we discuss eigenvalues. So the number is important. One way to understand it is as the slope of the determinant, or people like to say the infinitesimal version of the determinant, because you wiggle it by a very small number epsilon. But I mean, for now, if that seems kind of out of left field, you may prefer to just think of it as the sum of these two numbers and, vaguely remember in the back of your head that it has other important properties. Good. Thoughts or objections on this?
I do not believe I have any.
Okay. I now notice we're an hour in and Corbin has not surfaced, so perhaps it's good that we did not wait for him.
Yeah.
I cannot help but comment that I've done something very sneaky here, because this expression I've written down, which we haven't seen before, but the very first thing we're going to learn in Chapter 3, after you finish Consolidation Document 2, is something called the definition of the derivative. And this thing I've written down is exactly the derivative of the determinant I plus epsilon A. I mean, it's a preview, I guess, of the next thing we'll see in calculus is this definition of the derivative, which you may recall from the very first reading is supposed to measure slopes of tangent lines. But that's just kind of a teaser. Okay, good. Next. So you might ask, AD minus BC is this determinant thing. You're telling me this is the area. But what happens if AD minus BC equals 0? I can very easily cook up matrices with that property. So for instance, det P, the way that I've written it down here, det P, well, determinant is top left times bottom right minus top right times bottom left. And 1 minus the quantity minus 1 squared is 0. So how can it be that the image of the unit square has 0 area? Well, as we'll see on the next slide, there's something degenerate is the word we use. There's something degenerate about a matrix with 0 determinant, which is that it takes the unit square and maps it to a line segment, and a line segment has 0 area. So here I'll just do the two multiplications for you. So here's the example P. As we've seen, it has determinant 0. If I multiply this by 1, 0, I get the first column, which is 1 minus 1. If I multiply it by 0, 1, which is the unit of the y direction, I get minus 1, 1. So you would try to find the area of the parallelogram spanned by these two vectors. You would try. Unfortunately, what happens, here's what that actually looks like. So we took 1, 0, which I've written as u, so this is the vector in the x direction. And as you've seen, p applied to that gives me 1, minus 1, which is this vector here, 1, minus 1. Then I apply p to the y direction, to 0, 1, and it gives me this thing, minus 1, 1, which is here. So you would try to find the parallelogram whose vertices are kind of these points, and then in this case their sum, which is the origin. So you're trying to find the area of a parallelogram, which is kind of, you can think of it, if it helps you visualize, as like being very, very skinny, infinitesimally skinny, to use that word. So you would think if the determinant were not quite 0, but very close to 0, then the parallelogram would look like this. But as the determinant goes to exactly 0, then that parallelogram collapses. It's now just a line segment, which means the area is actually 0. Okay, is this argument that we collapse onto the line y equals minus x clear?
Yes.
Good, okay. So now I think the next one asks you a question about this, or a challenge. Yeah, so the next one I'll ask a challenge. Can we find a vector x, x1, x2, so that p applied to x is the vector 3, 5. So let me go back to here. What does 3, 5 looks like? So that's maybe 3 along x and 5 along y would be very large. So I don't know, there's some vector that goes way up here, for instance, which is 3, 5. So my challenge to you is, can you find a vector x so that px is the vector 3, 5?
Doesn't look like it's possible. Like just in multiplication.
Yeah, can you see geometrically why? Where is every single output of p applied to some vector? Where is that output guaranteed to lie based on this argument?
On the line y equals negative x.
Yeah, exactly. So we applied p to these two unit vectors, the basis vectors, 1, 0 and 0, 1. But every vector is some number times this first one plus some other number times the second one. So that means every output of p applied to some vector is going to be some number times this vector on the line plus some other number times this vector on the line, which means it's also on the line. So if every output of p applied to a vector sits on this line y equals minus x, we cannot possibly apply p to some vector x and get this vector 3, 5, which is not on the line. That's the geometrical reason that it's just not sitting on the line that p collapses you onto. The second way to see it is just algebraic, that you see the equation has no solution. So I think this is what you suggested. So if I have this applied to x1, x2 equals 3, 5, I get the two equations x1 minus x2 equals 3, and minus x1 plus x2 equals 5. And can you see quickly why these two equations cannot possibly have a solution?
Because attempting to add them results in 0 equals negative 2.
Good. Well, 3 plus 5 is 8.
Wait,
But
yeah. I can add.
Good. Yeah, these equations are inconsistent because their sum gives you nonsense. So these are the two ways to see that you can't solve the equation px equals 3, 5, or any real, actually you can't solve px equals any vector unless that vector is on this line. So this has no solution, which means that if you wanted to write down a general formula, maybe you wanted to solve something like px equals y, thinking of p as a function, p applied to x is some output y, you might try to solve this by saying, well, can we solve this by using an inverse function? That x is some inverse function, p inverse applied to y. So you might try to do that, but this argument shows that for this particular matrix P, that could never have worked. You cannot find an inverse function because applying that inverse function to this 3, 5, y, if you let y equal 3, 5, applying that inverse function to y would give you some x, but that x wouldn't actually satisfy this equation because we've shown no x satisfies that equation. So this matrix P is not invertible. You can't find an inverse function for it. And as we'll see in a moment, that's closely related to the fact that it has zero determinant. It's kind of like zero determinant means you collapse onto a line, and if you're on a line, you can't reach any vector, which is not on the line. Okay, thoughts on this?
Actually, I do have to give you a warning because right now it's 4:40 and I leave 4:55, and
Ah,
I have to pack up and stuff before I go to this one-person social event.
good, good. Okay, think there might be, I can probably, yeah, I mean, we have some algebra. I can skip this last proof. Okay, so the last proof is an kind of algebraic exercise to show that if the determinant is not equal to 0, then you can find an inverse. So maybe we can skip that since you have to leave, and I'll post the slides. But the result is that if the determinant is not 0, you can always find an inverse matrix, M inverse, and that involves dividing by the determinant, which is why you need to know it's not 0. So anyway, that's the last thing. There's a challenge related to the inverse, and you'll need to use inverse matrices